All right, for diagnosing our blower motor and all the components involved in it, we can start out by going to diagnostic view. First off, we should check. Granted, we have an LED lit here on the VFD, but do we have correct voltage supplied to the VFD, which would be 208, 240? Be our two red wires here. We go to volts. We can test that we have 240 volt. In the event that we didn't have the 240 volt, we would check our ice cube relay, which the coil voltage for that relay is from the blower motor internal thermal overload, as well as our power supply board. That power originates here for the coil voltage. So our ground of the 12 volts is here on the coil, while the 12 volts from the power supply board runs through the limit of the blower motor and then is returned to the coil. As long as that limit didn't open, this coil should be energized, allowing the one leg of power that is broken to get here to the VFD. We then have our 3 wires for our blower motor and our 3 wires for communication for fan speed. The VFD also has 3 fuses for each leg of power for the blower motor. So the VFD generates 10 volts communication voltage. It then sends it up here to the relay board, and then once the controller decides what fan speed we need, it returns back to the VFD, which then the VFD sends the correct voltage to the blower motor. So since we have power to our VFD, let's check our communication voltage at the relay board to see if it's leaving the VFD. Now, my probes here are too big to get in to this connection on that Molex. So we should be using needle probes. And this communication voltage is DC. Now, the blue wire, or this farthest position to the right, is ground, while our green wire is the incoming 10 volts DC, which here we can see we have that 10 volts DC. Red, or the first position on the left, is our return. This is our demand that the relay board is sending back to the VFD to run the blower motor at the correct speed. Now, in the event that this wiring harness, say the incoming 10 volts DC rubbed through the red one, which would be our return, that could complete the circuit and bypass the relay board, which means the blower motor would be running all the time without a call. So now if we go over to visual view, I can turn my blower motor on to, let's start at 10%. So at the board, now clearly I can hear the fans moving, but I can go on my return wire and my ground, and here I have fluctuation, but it was around DC. If I go up to 50%, go into my ground and my return, I'm reading 5 volts DC. Going to 100%, we should have 10 volts being returned. There we go, 9.9. So at 100%, the 10 volts that's leaving here is simply being returned for full power. Now we can test our motor to see if we're getting voltage in correlation to our fan speed. Now, if we recall, our wiring harness for our motor is right here with 3 leads. The VFD is actually generating 3-phase DC square wave. DC is a direct current, it's a straight line. Internally in the VFD, it shapes DC current to, it almost looks like alternating current at that point, which allows us to run a 3-phase AC motor through a single phase unit. So we'll go back to, we'll have to read it in AC volts. I will turn my motor to 10% and go between L1 and L3. I have 88 volts present. If I go to 50%, I have 168 volts. And if we go to 100%, I have 230 volts being supplied to the motor. We can check the other winding, L2 to L1, to find the same value. Back to 50% on L1 and L2, we have 168 volts. So at this point, we've confirmed we have power into our VFD. We confirmed we have the communication voltage generated at the VFD, sent to the relay board, and the relay board sending back the demand. And now we've confirmed that the VFD is generating voltage to the blower motor in correlation to fan speed on all 3 legs of power. Now, in the event the VFD has failed, I always recommend to confirm that the motor didn't take out the VFD, or vice versa. If the motor failed, let's confirm the VFD didn't take out the motor. At this point, we would have to de-energize the unit and ohm out our motor leads to confirm that it's not shorted to ground and our resistance is good. So again, we can use larger leads in the top, needle probes in this way if that's the route we were going, or we can go on the back side and go to the terminals. So by going to ohms, we'll say yellow's L1 to ground, no, nothing. L2 to ground, nothing. L3 to ground, nothing. L3 to L2, we have 7 ohms. L1 to L3, we have 7 ohms. L1 to L2, we have 7 ohms. So we're all within range. As far as this internal thermal overload goes, you could simply unplug the spades and check to confirm it's a closed circuit, which it is. If it was open, we would be at OL. The relay, very cut and dry. 12-volt coil voltage. 1 leg of power for the VFD. Comes in. The other leg of power goes to the VFD. It's a simple switch. One thing I forgot to mention is if we're not getting our 10 volts communication to our relay board, we can remove this wiring harness And very carefully with needle probes, first we would confirm the orientation of the color. So blue's on the left, that's our ground, green's our supply, and red's our return. So at this point I could test to see, I would go to ground, and then the middle wire pin, which would be our supply, to see if the VFD is actually generating the 10 volts. In the event that this wiring harness failed, it may prove that the VFD is fine, but we lost our connection between the VFD and the relay board.